So we are going to use the method of substitution to transform the Cauchy-Euler equation to a differential equation with constant coefficients to solve this third-order non-homogeneous equation. So the substitution here is x is equal to e raised t. Take ln on both sides, which would give us ln of x is equal to t times ln of e, which would mean t is ln of x. So the same process that we did previously. So we start by finding y prime, which is dy over dx. We could write this as d over dx multiplied, dy over dt multiplied by dt over dx. The way we can say it is I'm simply multiplying and dividing by dt, which would give us dt over dx times dy over dt. The derivative of t with respect to x is 1 over x because t is ln of x, multiplied by dy over dt. For convenience, I'm going to call dy over dt as yt prime. So yt prime is simply x y prime. Now we have to find y double prime, which is dy over dx, or d squared y by dx squared, which is d over dx of dy over dx. So we have d over dx of dy over dt times dt over dx. Now we have to use product rule. So we have d over dx of dy over dt multiplied by dt over dx plus dy over dt multiplied by d over dx of dt over dx. And that would give us d over dx multiplied by dy over dt is one over x, x times dy over dx, I believe. And dt over dx is 1 over x plus dy over dt multiplied by d over dx of dt over dx, which is 1 over x. Perhaps a better way to do this is to change the order of derivatives in this step. So I'm going to rewrite the first term. Going to bring d over dt and write it as dy over dx multiplied by dt over dx. You may ask me why, because I want the second derivative of y with respect to t. In other words, yt double prime, and this is the way to get it. So we would have d over dt. dy over dx is dy divided by dt multiplied by dt over dx, which is 1 over x, plus dy over dt minus 1 over x squared. So which would give us d over dt of dy over dt is d squared y divided by dt squared multiplied by 1 over x plus dy over dt minus 1 over x squared. So that would be am I missing an x term here? Dy over dt, missing a 1 over x term here. So y prime is 1 over x times dy over dt. So forgot to put that in. And that x is constant, well, 1 over x is constant, so it's going to come out. And we have 1 over x outside, so we have 1 over x squared. So we have yt double prime times 1 over x squared plus yt prime times minus 1 over x squared would equal y double prime. Multiply by x squared on both sides. X squared y double prime would equal to yt double prime minus yt prime. And that would be the second relationship. Now, since this is a third order differential equation, we've got to find the third derivative. So we have to take the third derivative of the second derivative. So the third derivative is simply d over dx of the second derivative that we have, which is 1 over x squared times d squared y divided by dt squared plus or minus dy divided by dt. Again, we have to use product rule. So d over dx of 1 over x squared multiplied by the second term plus d squared y divided by dt squared minus dy over dt times 1 over x squared multiplied by d over dx of d squared y divided by dt squared minus dy over dt. Okay. So I'd have to add a page. So the derivative of d over dx of x squared is minus 2 over x cubed. D squared y divided by dt squared is simply yt double prime minus yt prime plus 1 over x squared multiplied by d over dx, d squared y over dt squared minus dy divided by dt. Which I could write it as minus 2 over x cubed yt double prime minus yt prime plus 1 over x squared d over dx of d squared y divided by dt squared minus 1 over x squared d over dx of dy over dt. It requires a bit of finesse now. So we have minus 2 over x cubed. So yt double prime minus yt prime plus 1 over x squared d over dx d over dt times dy over dt minus 1 over x squared, change the order, dy over dx. So we have minus 2 over x cubed, yt double prime minus yt prime plus 1 over x squared d over, I could actually move the dt out, but before I do that, because I would like to have d cubed over d cubed y over dt cubed, and that's what I'm looking for. So the second part, I can move the dt out and have d over dx of dy over dt minus 1 over x squared d over dt. I know dy over dx is 1 over x, dy over dt. So minus 2 over x cubed, yt double prime minus yt prime plus 1 over x squared. Rewrite dy over dt again. I could write it as 1, before that we'll change the order here. If I change the order, I'd have d over dt times dy over dx minus 1 over x cubed d squared y divided by dt squared. So minus 2 over x cubed yt double prime minus yt prime plus 1 over x squared d squared divided by dt squared multiplied by dy over dx minus 1 over x cubed d squared y divided by dt squared. But we know dy over dx is 1 over x times dy over dt, so minus 2 over x cubed yt double prime minus yt prime plus 1 over x squared d squared divided by dt squared, 1 over x times dy over dt minus 1 over x cubed d squared y divided by dt squared. The 1 over x is not affected by the second derivative, d squared over dt squared, so I can pull that out. D squared over dt squared of dy over dt minus 1 over x cubed d squared y divided by dt squared. So minus 2 over x cubed yt double prime plus 2 over x cubed yt prime plus 1 over x cubed d squared y divided by dt squared dt is d cubed y divided by dt cubed minus 1 over x cubed yt double prime. Combine like terms, we will have 1 over x cubed yt triple prime, so 1 over x cubed yt triple prime, which would be that term, combining negative 2 over x cubed yt double prime and negative 1 over x cubed yt double prime, we get negative 3 over x cubed yt double prime plus 2 over x cubed yt prime. And that is equal to y triple prime. This would mean x cubed y triple prime is equal to yt triple prime minus 3yt double prime plus 2yt prime. So, in summary, what we have when we use x is equal to e raised t substitution, y prime, xy prime would simply be equal to yt prime. X squared y double prime would equal to yt double prime minus yt prime. X cubed y triple prime would equal to yt triple prime minus 3yt double prime plus 2yt prime. So this is quite standard. Anytime we use that substitution, we're going to change xy prime by yt prime, x squared y double prime by yt double prime minus yt prime, x cubed y triple prime by those terms. If we have the fourth order, we have to go one more step from here to get that done. But we have a third order equation, so I'm going to replace x cubed y triple prime, x squared y double prime, xy prime, and y and yt are one and the same. We've got to keep that in mind. So the original dE is x cubed y triple prime minus 3x squared y double prime plus 6xy prime minus y equals, I think it's 6y. So xy equals 3 plus ln of x cubed. Okay, so I'm going to rewrite that equation in terms of yt. So the first part would become yt triple prime minus 3yt double prime plus 2yt prime minus 3. X squared y double prime would be yt double prime minus yt prime. 6xy prime would be 6yt prime minus 6yt equals 3 plus ln of x cubed. Now, the homogeneous part is what we are interested in, so we're going to plug in 0 there. So the after simplification. So what we have here, yt triple prime minus 3 yt double prime plus 2yt prime minus 3yt double prime plus 3yt prime plus 6yt prime minus 6yt equals 3. I could go ahead and change the x. I know the substitution is e raised t, so I'm going to change it to that. So yt triple prime, by combining I have minus 6yt double prime plus 9 12yt prime minus 6yt equals 3 plus ln of e raised 3t. So now the equation is in terms of yt, and not only that, if we look at the coefficients, the coefficients here are constant, and that wasn't the case when we first started the problem. The problem was a Cauchy-Euler equation, which we turned into a problem with a linear differential equation with constant coefficients. It took us a lot of work to get here, and one may say, well, why should we even bother doing this? Well, sometimes this approach would be better, but other times we can simply use the Cauchy-Euler method directly. So what we have here now is a non-homogeneous linear DE with constant coefficients. So the associated homogeneous equation is yt triple prime minus 6yt double prime plus 12yt prime minus 6yt equals 0. The auxiliary equation is m cubed minus 6m squared plus 12m minus 6 equals 0. And if I pull the m squared out, I would have m minus 6. Let's see. Am I missing something here? I plugged in, simplified. It's not factoring the way I wanted to factor. Looks like, oh. That has to be 11 yt prime 2 plus 3 plus 6 is 11. Bad math. I don't think that is going to change our fate in any way, because I don't see this factoring in any form. So the only way is to do trial and error, but I would say use the calculator. You know, these days we can simply use a calculator to get the answer. So I don't want you guys to try manually. It's not necessary. So what I'm going to do is I'm going to plug in x cubed minus 6m squared, which is 6x squared, plus 11x minus 6. And if I graph this, oops, there are zeros. I could set the window from minus 10 to 10. And you can see that there are zeros. We could adjust the y-axis a bit more. Minus 5 to 5 perhaps. And narrow this down to minus 5 to 5 to get a better picture graph. Oh, that's neat. So you can see clearly the function is crossing the x-axis at 1, 2, and 3. Now, in this problem it is obvious, but if it's not obvious, you could always do second trace and select number 2 and press the arrow to pick a left bound, then move to the right bound after crossing the 0, and now you're going to guess between those two values, and we get x is equal to 1. So the roots are m1 equals 1, m2 equals 2, and and 3 equals 3. Unfortunately, we cannot factor this. So now that we have the roots, the complementary solution is yt, I guess ytc, is equal to c1 e raised t plus c2 e raised 2t plus c3 e raised 3t. It is not x raised m because we made the substitution, we changed it into a non-homogeneous linear DE with constant coefficients. So now we have to find the particular solution. Going back to the DE, yt triple prime, the original DE, minus 6yt double prime plus 11yt prime minus 6yt equals 3, plus the ln and e would get cancelled. I'd simply have 3t. So the three solutions for yt, solutions that are linearly independent for yt, y1 equals e raised t, y2 equals e raised 2t, y3 equals e raised 3t. So the Wronskian would be e raised t, e raised t, e raised t, e raised 2t, 2 e raised 2t, 4 e raised 2t, e raised 3t, 3 e raised 3t, 4 e raised 3t. Oh, sorry, bad math. 9 e raised 3t. Now we know we could pull out identical terms, so it's at 1, 2, and 3. Okay. So e raised t can come out, e raised 2t can come out, e raised 3t can come out, 1, 1, 1, 1, 2, 4, 1, 3, 9. Which would give us e raised 60, and the matrix 1, 1, 1, 1, 2, 3, 1, 4, 9. That would be W, which would imply determinant of W is e raised 60, 1 times 18 minus 12, minus 1 times 9 minus 3, plus 1 times 4 minus 2. E raised 60, 6 minus 6 plus 2, you get 2 e raised 60. Now that is simply the determinant of the Wronskian. Now that we have the determinant, we can it didn't specify to use variation of parameters, but I'm just using variation of parameters here. Of course, which one would be an easier method, variation of parameters or annihilator approach? Let's see. We have ax plus b. A simple annihilator would be d squared. That would take care of both, which would give us solution as 0 and 0. So we would end up having, I think, Well, variation of parameters is great, but I'm thinking that we could do this problem easily with superposition. It didn't specify in the problem to use variation of parameters, so why make things complicated? Okay, so this is why we learned all the other methods, so we can either do the annihilator approach or we could do the superposition approach. Let's go with the annihilator. So if I write this from the solution, the dE is simply d minus 1, d minus 2, d minus 3, yt equals 3 plus 3t. I want to annihilate 3 plus 3t, and it would be annihilated by d squared, d minus 1, d minus 2, d minus 3 yt equals d times 3 plus 3t. So yp is of the form yp for t actually, so I'll just call it ytp. The particular solution for yc is of the form c1 e raise 0 plus c2 t e raise 0x. Actually, t. So ytp is c1 plus c2t. Now we have to find the derivatives and plug it in. So ytp prime is c2, ytp double prime is 0, ytp triple prime is also 0. Let's plug in c1 and c2. Oh, well, this c1 and c2 are for the particular solution. Maybe I should call it d1, d2. d1, d2, d1 plus d2t, and that would be d2. So if we plug everything in, we have 0 minus 6, yt double prime, which is 0, plus 11 d2, minus 6, d1 plus d2t. That would equal 3 plus 3t. So 11 d2 minus 6 d1 plus d2t equals 3 plus 3t, which would imply d2 is simply 3. 11 d2 minus 6 d1 is equal to 3. So 11 times 3 minus 6 times d1 equals 3. Minus 6 d1 equals 3 plus 33. d1 is 36, and minus 6. We have d1 equals 1 over 6 with a negative. Oh, my bad. We made a mistake here. It should be minus 6 d2, which would mean, 3 over minus 6, which would give us minus 1/2. That changes everything. So 11 times minus 1 over 2 minus 6 times d1 equals 3. Minus 6 d1 would equal 3 plus 11 over 2, which would mean d1 is 6 plus 11 over 2. Divide by negative 6, we have 17 over 12 with a negative. So the particular solution for yt is ytp equal to d1, which is negative 17 over 12, plus d2 is minus half, so minus half t. So the solution to yt is yt equal to the complementary solution, which is c1 e raised t, c2 e raised 2t, c3 e raised 3t, minus 1 half t, minus 17 over 12. Now, if that is the case, the solution to y is obtained by substituting t equals ln of x. That is the substitution we had at the very beginning, several pages ago. It's right over here. So y would be equal to c1 e raised ln of x, c2 e raised 2 ln of x, c3 e raised 3 ln of x, minus 1 over 2 ln of x, minus 17 over 12. c1 e and ln would get cancelled, we get x. c2 e raised ln of x squared, c3 e raised ln of x cubed, minus 1 half ln of x, minus 17 over 12. The e and ln would get cancelled. c1x plus c2x squared plus c3x cubed, minus 1 half ln of x, minus 17 over 12. And that would be the solution to y. Key things to note in this problem. This summary over here is not going to change when we use the substitution. So you don't have to derive this over and over again unless we go to fourth order derivatives, in which case we have to start at the third derivative here and then derive for the fourth derivative. So this is a given. You don't have to redo it. And of course, don't make bad algebraic mistakes like I did. And this is a third order Cauchy-Euler equation. We only did the derivation for second order. Of course, there is a derivation for third order, but I'm not going to go over it. We'll just use this process, and people would do this process to get the fourth order, fifth order, and so forth. So we make the substitution, we convert it to an equation with constant coefficients, we solve it the usual way. Particular solution, initially I started doing variation of parameters, then I looked at the right hand side and realized variation of parameters might be too much for this problem, so I stuck with the annihilator approach. Let me make a note of it here. And the annihilator here that I used is d squared. And d squared we know is going to annihilate both, that's a d squared, the constant as well as 3t. And you get a particular solution for yt, combine the complementary and particular solution, and use the substitution to get back to the solution for y. So here we have a case where we have to use the substitution y is equal to x minus x naught raised m to transform the Cauchy-Euler equation to solve the differential equation. So obviously x sub 0 here, by the looks of it, is 1. So you can see we have x minus 1 squared and x minus 1. So that's a giveaway that x sub 0 is equal to 1. So what we have is y is equal to x minus 1 raised m. Now we want to find y prime and y double prime and so forth. This is a second order equation, so maybe we just start with m equals 2, but we can deal with that later, I suppose. So I am going to do y prime, which is m, times x minus 1 raised m minus 1. Y double prime is m times m minus 1 times x minus 1 raised m minus 2. Plug in the equation, so plug in y prime and y double prime in x minus 1 squared, y double prime minus x minus 1 y prime plus 5y equals 0, which would imply x minus 1 squared. Y double prime is m times m minus 1, x minus 1 raised m minus 2. Of course, we've got to multiply by y at the end, minus here x minus 1 times m times x minus 1 raised m minus 1 plus 5y equals 0. You can see that the m minus 1 squared, x minus 1 squared and x minus 1 raised negative 2 will get cancelled. So I'm going to write it this way. Y is x minus 1 raised m. So those two would get cancelled. So we have m times m minus 1 multiplied by x minus 1 raised m minus x minus 1 raised m times m plus 5y equals 0. And what x minus 1 raised m is y, so m times m minus 1y minus y m plus 5y equals 0. Divide by y on both sides, we have m times m minus y minus m plus 5 equals 0. If I FOIL, I'd get m squared minus m plus 5 equals 0. This would give us m squared minus 2m plus 5 equals 0. And that is simply the auxiliary equation corresponding to the Cauchy-Euler equation that is given in the problem, x minus 1 squared y double prime minus x minus 1 y prime plus 5y equals 0. So this is why deriving and understanding the process with the Cauchy-Euler is quite important, because we could not have picked this up directly from the problem itself. So the auxiliary equation is m squared minus 2m plus 5 equals 0. This would imply the roots are m1. Let's see if we can factor this. We have 5 and 2. Perhaps not. No. So quadratic formula, minus b plus or minus b squared minus 4ac ac divided by 2a plus or minus square root of 4 minus 20 divided by 2. So we have 2 plus or minus square root of negative 16 over 2. 2 plus or minus 4i over 2. We get 1 plus or minus 2i. So we have the two roots which are conjugate pairs, 1 plus 2i and 1 minus 2i. This would imply alpha is 1 and beta is 2. So the complementary solution, is there's a homogeneous equation? Yes, luckily. So the complementary solution is y equals c1 x raised alpha. Should probably put we made a substitution initially as x minus x naught. So in our standard case, instead of x, we have to have x minus 1 raised alpha, which is 1, multiplied by cosine beta, which is 2, ln of x minus 1, plus sine beta 2 ln of x minus 1. And I put the constants in the wrong place again. C1, C2. So the solution is simply x minus 1, C1 cosine ln x minus 1 squared plus C2 sine ln x minus 1 squared. And that is it. It's the same process, but instead of x raised m, we have x minus x naught. So we have to replace x by x minus 1. So here we have t is equal to x minus x naught substitution. And we have to transform the given equation to get the solution. You should have recognized what that x naught is going to be. X naught here is 2. We have x plus 2, so x naught would be negative 2. So we have a different type of substitution where t is x plus 2. In the previous problem, we simply had the solution to be equal to x minus x naught raised m. Of course, that method would work. This is just a different way of doing the problem by creating a dummy variable. So that is our substitution. So we start with dy over dx, and that would be dy over dt times dt over dx. So dy over dt multiplied by d over dx of x plus 2, which is simply 1. So dy over dx is equal to dy over dt. Now we have to find the second derivative, because the second derivative is playing a part in there. So d squared y divided by d squared would give us, I'm going to call that yt. Going to change it and call it as yt prime because we have dy with respect to dt. So this would be d over dx times dy over dx. We already know that that is dy over dt. I could change the order and write it as d over dt, dy over dx. But dy over dx is simply dy over dt. So d over dt, dy over dt, which would give us d squared y divided by dt squared. That simply is yt double prime. So the original dE is x plus 2 squared y double prime plus x plus 2 y prime plus, I believe it's y, yes, y equals 0 becomes, I'm doing a substitution, t squared, y double prime is simply yt prime, sorry, yt double prime, t yt prime plus y equals 0, or yt. They are one and the same in terms of substitution. Now that is a Cauchy-Euler equation in t. Instead of x squared, we have t squared, matches with the derivative. Instead of x, we have t, matches with the derivative, and we have yt. And second order. So we know the auxiliary equation is am squared plus b minus am plus c equals 0. That goes back to the very, very first step. A here is 1, b is 1, c is 1. Plug that in. The auxiliary equation is m squared plus 1 minus 1m plus 1 equals 0, which would imply m squared plus 1 equals 0. M squared would be equal to minus 1. M is plus or minus square root of negative 1. So the roots are conjugate powers. m1 equals I and m2 equals minus I. Which would simply imply alpha is 0 and beta is 1. So the solution to yt is yt equal to t raised alpha c1 cosine beta ln of t plus c2 sine beta ln of t. Alpha is 0, t raised 0, c1 cosine b is 1, ln of t, plus c2 sine beta is 1, so we have ln of t. But our substitution is t equals x plus 2, which would imply y equals c1 cosine ln of x plus 2 plus c2 sine ln of x plus 2. Sorry, it's actually x minus 2. Let's go back. Is it x plus 2 or x minus 2? Nope, x plus 2. So, x plus 2. So, we could have done the same problem using the substitution that we had in the previous problem. We would get the same answer, but you can pick and choose. I believe that this one requires extra steps. Here we just reduce the equation to a Cauchy-Euler equation and use the standard formula and end up getting the solution for yt. Revert the solution for yt by putting the substitution back, so we get the solution for y.